We're going to talk some more about integrating products of trig functions. Specifically, we're going to look for a formula because we found when we integrate these products it's a very lengthy process and we're going to be repeating similar steps over and over. So having a formula is going to be helpful. And we're also going to consider integrating tangents, cotangents, secants, and cosecants. So what if we had the integral of sine to the 6th x dx? We know from what we've seen that we could do this, it's a sine raised to an even power, so we could do this using the half angle formula, but it would require multiple steps of doing that. So what if instead we computed the integral of sine to the nx dx, where n was a positive integer, and we're going to come up with a formula. So to start this, we're going to split off one of the sines. So this is n minus 1x, and then the sine x that we're splitting off, dx. Now we're going to integrate by parts, and this is going to be our u, and this is going to be our dv. So we have u is sine to the n minus 1 x, so our du would be power out in front, n minus 1, decrease the power by 1, so sine to the n minus 2x, and then chain rule multiplied by the derivative of what's inside, so cosine x dx. And then our dv was sine x dx, so our v must have been negative cosine x. Now recall our integration by parts formula said if you have the integral of u dv, that equals uv minus the integral of v du. So let's go ahead and apply that here. So we have uv, so we're going to have negative sine n minus 1x cosine x minus integral of v, negative, and it's going to be multiplied by du. So we have this negative cosine x multiplied by this, so that's going to be n minus 1 sine n minus 2x, and we've got two different cosine functions, so cosine squared dx. Now let's see what we can do to simplify this. We could combine those two, make that positive. This is a constant, so we can move that out in front. And then we can also replace this with the Pythagorean identity to get it in terms of sine. So we have negative sine to the n minus 1x cosine x plus n minus 1 out in front of this integral of sine n minus 2x multiplied by 1 minus sine squared x dx. So let's see what we can do with this. Now when we started this, we started out with it being equal to this integral of sine to the n x dx. So let's put that first. We've got the integral of sine to the nx dx, and we found that is negative sine to the n minus 1x cosine x. Now I'm going to distribute this through, and I'll have two terms, and so I'm going to split up the integral. So the first of those is plus n minus 1 integral of sine n minus 2 x dx, and then the next piece, when I multiply this one to this one, it's going to have a negative on it. We've got n minus 1 integral, and so I add the exponents, so I have n minus 2 plus 2, so that's going to just leave me sine to the n x dx. Now what we have is this integral and this integral match, so I'm going to move this one over to the other side. So if I have them over here under the same integral, I have the sine n x, and then if I move this over, I'm going to have plus n sine to the n x, and this one would be a plus, which moved over to make minus sine to the n x, and all of this is dx, and that will equal my negative sine to the n minus 1 x cosine x plus n minus 1 integral of sine to the n minus 2x dx. Now we can see that these two would cancel, and this n is a constant, so I could divide both sides by n. We'll do it over here like this. And what I am left with is a formula when I have the integral of sine raised to some positive integer power dx. And what it equals is negative sine n minus 1 x cosine x, and that's divided by n, plus n minus 1 over n times the integral of sine n minus 2 x dx. So what this is a formula that still leaves me an integral, but when I start out with sine raised to the nth power to integrate, I end up with an integral that is 2 less in power. So it's a formula that I can apply to reduce the power on it. Now if I was applying it to a 6, I would apply it and I would still have an integral with a sine raised sine x to the 4th power, but then I could apply it again and end up with 1 raised to the 2nd power, and then I could apply it again. Now in the examples we will do a sine to the 6th x using that formula. So this one and its similar process can be done for the other trig functions of cosine, tangent, and secant, and they are called reduction formulas because you start out with n, a positive integer, a power on one of these trig functions, and you reduce the power by 2 by using these formulas. And you can continue then to apply the formulas until you are down to a 0 power or you're down to a 1st power, which you can integrate. Now let's consider if we had the integral of tangent x dx. We could express tangent in terms of sines and cosines. So tangent is sine x over cosine x, and then we have dx. And we could express this as cosine to the negative 1x sine x dx, and then we can see that a u substitution would work. So we could let u be cosine x, and then du would be negative sine x dx. And so we already have the sine x dx, so negative du would be sine x dx. So this is going to be the integral of u to the minus 1 and a negative du. Negative natural log of absolute value of u plus a constant. And so we could express that as negative natural log of cosine x plus a constant. So this would be the integral of tangent x. We can actually do one other thing using log properties, and we could take this out in front, which is a negative 1. We could move it up here, and then that would be the natural log of 1 over cosine x plus a constant. So we could express that as the natural log of the absolute value of secant x plus a constant. We could do a very similar derivation for cotangent x, because the integral of that, because it would just be a reciprocal thing. We'd do a similar thing. So the integral of tangent x dx is negative natural log absolute value of cosine x plus a constant, or could also be expressed as the natural log of the absolute value of secant x plus a constant. And cotangent ends up being very similar. There's going to be a different sign on it and the opposite trig function. So natural log of absolute value of sine x plus a constant. Now we want to consider finding the integral of secant x dx, and this one's going to involve a little bit of a trick in knowing what to multiply by. So we're actually going to multiply by, well, it's going to be 1, but it's not going to look like 1. We are going to multiply by secant x plus tangent x over secant x plus tangent x, because anything over itself here like this equals 1. Okay, now why would we do that? Well, let's see what happens, and then it will become apparent in a minute why we would want to do that. So in the numerator, we're going to have secant squared x plus secant x tangent x, and then denominator we've got secant x plus tangent x, and then dx. Now we're going to do u substitution, and we're actually going to let our u equal that denominator, secant x plus tangent x. So our du is going to be the derivative of secant is secant tangent, so secant x tangent x, and then plus the derivative of tangent is secant squared x, and then we've got our dx, and would you look at that? There's our numerator. So applying this substitution, we have du over u. Well, that's just the natural log of u plus a constant. So substituting for u, we have the natural log of u was secant x plus tangent x in absolute value plus a constant. So the integral of secant x dx is natural log of absolute value secant x plus tangent x plus a constant. We could do a very similar thing for cosecant, and we would find it has the negative and then has the cofunctions there. So let's think of what we might do if we had products of tangents and secants. Now, one of our strategies when we had sines and cosines with an odd one was we split off a sine or a cosine because that became my du. But looking here, thinking of the derivative of tangent, it is secant squared. So what I'm going to want to do is I'm going to want to split off not a secant but a secant squared. So this would leave me secant squared x split off a secant squared x dx. Now how that helps me is if I did a u substitution, I could let u be tangent x, and my du is going to be secant squared x dx, which is right here. But I want to write this secant squared x in terms of tangent, and I can do that with the Pythagorean identity again. So I'm going to have the integral of tangent cubed x. This is tangent squared x plus 1, and then our secant squared x dx. So expressing that in terms of u, that is u to the third and u squared plus 1 du. Well, so that's just the integral of u to the fifth plus u to the third du. So we have 1/6 u to the sixth plus 1/4 u to the fourth plus a constant. So that's going to be 1/6 tangent to the sixth x plus 1/4 tangent to the fourth x plus a constant. So let's look at another one that's the product of a tangent and a secant. And our strategy of splitting off a secant squared, because it's the derivative of tangent, is not going to work here. And if we tried to go the other way and think, well, maybe the derivative of secant is secant tangent. So I still don't have enough secant functions here to do that. So instead, I'm going to use a Pythagorean identity, and I'm going to replace this and get it in terms of a secant. And so that would be the integral of, this would be secant squared x minus 1, and then multiplied by secant x dx. And so if we distributed that through, we would have the integral of secant cubed x minus secant x dx. Then from here, we could resort to a couple of formulas that we came up with earlier. We have the formula for the integral of secant, so we could apply that here. And we also have a reduction formula for secant, so we could apply that here with n equaling 3. So if we do that, let's go ahead and do this part first. So we would have secant, and n was 3, so 3 minus 2 is 1. So secant x tangent x over 3 minus 1, so that's going to be 2, plus 3 minus 2 is 1, 3 minus 1 is 2, and then the integral of 3 minus 2, so that's going to be secant x dx. So that's working this first part, but then, oh wait, look, we already had minus the integral of secant x dx right here. So we could combine these two and then go ahead and use what we found the integral of secant to be. So it looks like our final answer is going to be secant x tangent x over 2. Combining these would be minus a 1/2, and then applying this would be natural log of absolute value of secant x plus tangent x and plus our constant of integration. And of course, instead of writing this over 2, we could put the half out in front if we wanted to. So let's summarize. If we have the integral of the product of tangent to some power, secant to some power, we're going to look and see if the power on the secant is even. If so, we're going to split off a secant squared and then write the remaining secant using the Pythagorean identity to get it in terms of tangent and let u be tangent of x, and we'll be able to work the integral. If the power on the tangent is odd, we could split off a secant tangent and then write everything in terms of secant, because the derivative of secant is secant tangent, and then do a u substitution with u being secant x. If, however, n is odd and m is even, so our power on our tangent is even and the power on our secant is odd, then we are going to do what we just did, which was express that even-powered tangent in terms of secant using the Pythagorean identity and then apply the reduction formula.